Hello guys, today I've got something a little different for you. What I have here are two GY712 current sensing modules. My plan is to use these just to monitor some currents coming on a few solar panels that I'm just experimenting with at the minute. Only small ones, probably like 5 to 20 watts, so nothing too crazy. But I have two modules here. One is a 5 amp version and one is a 20 amp version, and we're just going to take a look at how they work. So the module itself is pretty simple. It's just an ACS712 current sense chip and a couple of capacitors, all on a PCB, just with a header and this little connector here, connector block. I wouldn't be a big fan of these terminal blocks, just because you can see here on the bottom these pins are offset and they're a little flexible. So when you solder them in, you can see that the little block kind of wobbles a bit on the board. So I don't particularly like that. I'm going to be mounting these, probably I might mount them on a PCB, or I might just mount them on a piece of wood. But what I'm going to use are brass standoffs. So what I think I'll do to connect the wires is just to put the standoff on the back to my piece of wood. So that'll mean I can get 4 screws into the board here, and that'll hold it nice and steady. And because I'll have a 3mm bolt here, I think I'll just get some crimp terminals, 3mm ring type ones, so that I can just put it on there, screw it down nice and tight, and everything will be fixed in place nice and tight to the, well, whether it's a PCB or a maybe just a thin piece of wood, I'm not sure yet. I'd be planning to have a couple of these mounted so that I can measure the currents coming from a few individual panels, and they'll all be feeding back to a microcontroller, which I think will be an ESP32 module. But that's the way I'd prefer to do it. If you were going to use these screw terminals, just be careful not to twist the screwdriver too tight, or you could end up breaking a terminal, which kind of would ruin your day, I guess. You could also get like spade terminals for these crimp terminals. You could crimp and then just push them in, screw it down to tighten it. But I don't think it would take much to flex these, so just be careful. So the idea with this module is that you install it in series with your wire. So you would cut your wire in, well, wherever suits you really, and you'd connect one end here, one end here. The current would come in along this trace on the PCB. See it a little bit better. So along this trace on the PCB goes to these pins on the chip, goes through the chip and out on the 2 pins on the other side, and along this trace. And as it passes through the chip here, the current flowing in the wire inside the chip generates a little magnetic field, and the sensor inside the chip can pick that up and convert it into an output that our microcontroller can read. So it's pretty simple. I'm not sure how accurate it'll be, but we'll give it a go and see. So what I'll do now is wire it up to some sort of a load, and we'll feed it with 12 volts, just because the panels that I plan to use are going to be for 12 volt system. It'll be, the panel will be 18 volts really, but it'll be charging a 12 volt battery. And when we have it hooked up to the load, we can measure our output voltage and just see what these kind of things are actually doing. And we'll compare it to the multimeter just to see if they're accurate at all. Okay, to test this out, we have our 5 volt supply here. That's going to provide the VCC to our chip that we're testing here, our ACS712. For a load, I have a string of LED lights, and I just have a 12 volt power supply here. So you can see the voltage on our multimeter here. That is the output voltage. So if I give it power, we've now supplied 5 volts to our module here. This is a bidirectional chip, so what you get is the voltage is going to be in the middle of our 5 volts. So maybe if we probe the 5 volt line, it will be slightly under 5 volts. Let's just check that. So our voltage is actually 4.96 volts, and from our sensor we're getting 2.49, so it's a little bit under the 5 volts. Probably if we had exactly 5 volts we might be getting exactly 2.5, but it's close enough. That's because there's no current flowing at the minute, so there's no current flowing in this direction and no current flowing in this direction. So when we add the power to this, current is going to flow in this direction, and we'll see the voltage either go up or down when the lights are on. So if we add our power here, so the voltage has dropped because the current is flowing. So if I get my calculator now, our voltage has dropped by around about 0.5 volts. Our module here is the 5 amp version, so the change for it is 185 millivolts per amp. So we divide our 0.5 volts by 0.185 for 185 millivolts. So that means that our current is around about 2.7 amps at the minute, going to our string of LEDs. So they're heating up. Better take the power off that, let it cool down a bit. So 2.7 amps going to the string of LEDs is probably reasonable enough. We'll check that after with the multimeter directly. So what's happening with the module here is when you get a current flowing through a wire, it generates a magnetic field, and with this module the wire comes to the terminal here, it goes down into the chip, through the chip, back out to this terminal. So there's a magnetic field being generated on that wire as it passes through the chip, and there's a little sensor in the chip that can convert that magnetic field that it senses into a voltage between our 5 volts that we've supplied between ground, or positive and ground. So that's what you're seeing on the output. It's the output of that little sensor that's sensing the magnetic field. So you might have noticed as we bring the screwdriver towards our sensor, the magnetic field is changing. There's probably a magnet in the tip of this screwdriver that's causing that fluctuation there. So if I swap these two wires, we should be able to see that the voltage will increase on the sensor. So I'll do that now. Okay, well that's the wire swapped around. Probably not great connections, but we'll see what happens. So now that we've switched the wires around, you can see the voltage increased this time, and it's increased by pretty much the same, so it's going to be around about 2.7 amps being measured again. So the next thing I'll do is just swap to the 20 amp version and see what we measure from that one. Okay, now we have the 20 amp version hooked up here. So it's basically the same, except it's going to be able to measure up to 20 amps in both directions. So when we give it the 5 volts, we are again at 2.49 volts, which is what we would expect. It's the same chip, just for the higher ampage. And again, you can see the variation with the magnet coming close. It's not as much now because obviously the range is much higher now, so it would take a bigger magnetic flux to change the voltage on this version of the module. So let's power it up again. We are at 2.2 volts there. 2.49 minus 2.22, our change is 0.27. This time we're going to divide that by 0.1 because it's 100 millivolts per amp. So obviously that's coming out to 2.7 amps. And that's the same value that we got the last time. So that's pretty good, the two match. The last thing to do, I guess, probably not really much point, but we'll test it with the multimeter just to confirm it's given the same result. Okay, just a final test to compare the results. I have the same load and the same power supply. It's just hooked up to the multimeter this time instead. So if we give it power, the multimeter is actually only showing 2.2 amps. So quite a bit lower than our first test had shown with the two sensors here. So these two sensors are pretty close to each other, but they're not matching the multimeter here. It's probably not too surprising that these modules wouldn't be 100% accurate. They are, after all, only a couple of dollars for everything, including a connector, headers, PCB, 2 capacitors and the chip. So you know, you have to take it with a little bit of pinch of salt, I guess. You could try to calibrate your microcontroller's reading using your multimeter. So if you had a load, you could have your multimeter in series with the load, so it would be reading amps at the same time that this was reading the amps. Then with your microcontroller you could fine tune your millivolt to amp reading. That might improve your results, but you'd need to have a load that you could adjust up and down so that you'd have a few different points. You couldn't really do it with one load, because you would tune it for, say, this 2.7 amps to 2.2 amps. You get that perfectly right, and then you put half this load on, and then you might see that your current doesn't match again. So you would have to fine tune it a little bit with a load that you could maybe adjust, or have a couple of different loads just to test it at different current. So I plan to use a few of these to measure currents on a few solar panels. Nothing too special, only little small solar panels, and I just want to see what happens when some of the panels are loaded during the day, or they're in shade, different things like that. So that's all I'm going to use these little modules for. But I'd say they're pretty handy. Probably not the most accurate, but to give you an indication of what's happening, and that's probably all you're looking for. So if you liked the video, don't forget to hit the thumbs up and get subscribed, get the bell on, all of that stuff. But that's all I have for today. I hope you've enjoyed the video. Thanks very much for watching.